to my seminar, and I'm John Leon, and I will, the subject of my seminar will be the adsorption of rare elements on aluminium and iron oxyhydroxysulfates under the conditions of acid mine drainage impacted Estuary of Huelva. So, to warm up a little bit of acid mine drainage. The acid mine drainage is a water or is a liquid of and is a direct consequence of the oxidative dissolution of iron sulfides, which are pyrite, chalcopyrite, arsenopyrite, and pyrrhotite. Well, in this dissolution, three main processes occur. One of them is the oxidation of iron 2 to iron 3. The other one is the oxidation of reduced sulfur to sulfate. And the third one is the decrease of the pH to values of between 2 and 3. So these are three reactions, the three main reactions of oxidative dissolution of pyrite. In the first one, we see that pyrite gets oxidated by oxygen and generates iron 2 and sulfate and a bit of acidity into the water. The other one is the oxidation of iron 2 to iron 3, which consumes a bit of acidity. And the third one, which is the most important, is the oxidation of pyrite due to iron 3 that generates a lot of acidity. The acid mine drainage in the Iberian Peninsula is mainly located in the Iberian Pyrite Belt. It is an extensive metallogenic region located at the southwest of the Iberian Peninsula, and most of the acid mine drainage in the basin discharge at the Estuary of Huelva. In the Iberian Pyrite Belt, the total rare earth elements concentrations reach from 1,000 to hundreds ppb, and this is due the rare earth elements are in trace concentrations and sulfides that I mentioned earlier. In the Estuary of Huelva, these acid mine drainage get mixed with seawater, and the result of this mix is a neutralization of increase of pH, in the estuary we can find a pH range of 2.9 to 8.2, which is seawater. We also have different changes in salinity as you get more mixed with seawater. So this is, for example, the estuary, the part of the Rio Tinto, and here in these points we find the pH around 2.93, and as we get close to the sea, the pH increases to a maximum of 7.82. So, sorry. Well, a brief introduction also for rare earth elements. The rare earth elements are all of these. They are divided into light rare earth elements, middle rare earth elements, and heavy rare earth elements. Light rare earth elements are lanthanum to neodymium, to samarium, and then these are the middle rare earth elements, and these are the heavy rare earth elements. In this in this study, I picked lutetium as an example of heavy rare earth elements, gadolinium as an example of middle rare earth elements, and lanthanum as an example of light rare earth elements. And yttrium and scandium, also they are included in this group, and I will also explain them. So, rare earth elements are also raw materials for technological development. They are also emergent contaminants that can put that put in risk environmental and human health. And they are also used in geochemistry as an indicator of geological processes that may involve their partitioning. In the crust, it is relatively difficult to find rare earth elements in minimal concentrations. For example, in China, nowadays China owns 54% of the production of these elements. So, going back to acid mine drainage, schwertmannite and basaluminite are one of the two minerals we will be discussing this today in this seminar. They are respectively iron and aluminum oxyhydroxysulfates. They precipitate during the neutralization of acid mine drainage. Here we can see a picture of an acid mine drainage mixed with a natural stream. The orange precipitate is schwertmannite, which precipitates at pH 3.5, and this whitish layer is basaluminite, which precipitates at higher pH. So as it gets mixed with seawater, there is sequential precipitation of these minerals. Since we are working, these minerals can potentially retain rare earth elements via chemisorption, and they optimally retain these rare earth elements at circumneutral pHs. So in the estuary, we have these changes of pHs that may involve in adsorption of rare earth elements, but in these conditions, we have no data of the effect of the ionic strength on the capacity to retain the rare earth elements in these minerals. So the objective of this study is to see the effect of the ionic strength on the capacity to retain rare earth elements, sulfates. They are species onto these minerals. To do that, we will perform large-scale experiments. We will also obtain the equilibrium constants of the adsorption reactions at different ionic strength. We will compare them, and we will model the experimental results to see if our thermodynamic data adjusts to reality. We will also use synchrotron energy to determine possible changes in the structure of basaluminite that is exposed at high ionic strengths. We will perform high energy X-ray diffraction in pure and reactive basaluminite, and also we will perform extended X-ray absorption fine structure in unreacted basaluminite. So if we go to the back experiment, they are quite simple. We have used three solutions that will react. The solution 1 and solution 2 have more or less the same content of rare earth elements and sodium sulfate, but different content of sodium chloride, which gives us different ionic strength. The solution 3 has 5 ppm of lanthanum and a lot of sodium chloride. This is because we want to force lanthanum to generate a chloride species to see if this chloride can be absorbed onto the surface of basaluminite, which ended up that it doesn't. So we will mainly focus in solution 1 and solution 2. These two solutions were mixed with schwertmannite or basaluminite with a solid liquid ratio of 1 gram per liter, and then they were shaken for 6 hours at different pH depending on the liquid and at standard conditions regarding to temperature and pressure. So this is the speciation of the solution 1 and solution 2. The main difference we can see here is that the rare earth element sulfate, which is the species that is absorbing onto the surface of the minerals, is higher in solution 1 than in solution 2. And on the other hand, the solution 2 has higher free ion species and higher aqueous rare earth element fluoride. So the results of the absorption here in basaluminite, this is solution 1 and solution 2. We don't see much difference from one another. We see in both that the adsorb fraction increases as the pH increases also, and we see that heavy rare earth elements, which is for example the tethym, are more adsorbed than light rare earth elements, which is for example aluminum, and middle rare earth elements, of course, they are in the middle. We also see that scandium has a different behavior. It is almost completely adsorbed at pH 5, in which the rare earth elements are barely absorbed. The other rare earth elements are barely absorbed. The same happens in schwertmannite. We see the same pattern with scandium, and we see an increasing adsorb fraction as the pH increases. We also see that light rare earth elements are less adsorbed than heavy rare earth elements. So, to model this adsorption reaction, we have first defined an adsorption reaction, which is this one. This reaction is rare earth element sulfate in an aqueous environment, reacts with n numbers of free sites of the mineral, and it gives us an occupied site plus n protons. This reaction has an equilibrium constant associated. This equilibrium constant has to be expressed this way because the free sites and the occupied sites are limiting factors in the reaction. So they will be expressed as a molar fraction between the concentration of the occupied sites and the total concentration of the sites. The same happens with the free sites, which are expressed as the total concentration of the sites minus the occupied ones. So if we apply these changes and express this equation as a logarithm, we can make a linear equation in which n is, which is the number of the occupied sites, is the slope of this linear expression. So, well, this n, if we plot our data and make a linear regression, the slope might be 1 or 2. If it's 1, the reaction will be monodentate and we will use only one side. If it's 2, will be bidentate. Well, in reality, it can be in the middle, which, for example, in the linear regression of schwertmannite, solution 1 and solution 2, we see that the values are between 1.3 and 1.5. So this is between 1 and 2. So our guess would be that they are both reactions occurring in this in the surface of schwertmannite. So in order to take to extract the thermodynamic data, we have to use a software and force the slope to 1 or 2 to obtain the equilibrium constant for the reaction of each number of sites, each n value. These are the reactions. It's a very big table, I'm sorry. But basically, we see that a different ionic strength for bidentate sites, we have similar values of log K at different ionic strength and also at monodentate reactions. So in this case, what we can conclude is that the ionic strength has no effect on the capacity of this mineral to retain the rare earth elements. If we plot this data, if we plot our experimental data with and compare it with our models, we see that our experimental data and our model match quite well. So we can also say that these two, we have implemented both reactions, and with both reactions we see that it is a good match. So both reactions are occurring in the surface. So regarding to basaluminite, it is a more difficult mineral, but we see that the values are around 1. So bidentate reactions are not occurring at the surface of this mineral. And if we compare the values, they are more or less in the same order of magnitude. So we could say that for this mineral, also ionic stress doesn't have any effect. The models for heavy rare earth elements, which is lutetium, match quite well with monodentate reactions, but with lighter rare earth elements, they don't match pretty well, but they do more or less the same tendency. So when we skip to EXAFS modeling, first I will make a brief explanation of the EXAFS. So basically, with EXAFS, we irradiate a sample with an X-ray with a certain wavelength that to an atom of to the sample. This wavelength will target specifically one electron in an orbital, and it will get excited and will interact with. Leave the orbital and interact with the nearby atoms, and when it returns, it will leave us some spectra that will have interatomic atomic information, well, molecular information. So to first know what's happening, we have to guess how is gadolinium adsorbed, and our initial approach is that the coordination number of gadolinium, which is the number gadolinium oxygen path, is 8, which is the number of oxygens that are surrounding our gadolinium. This is the tetrahedron of sulfate, and these are 2 octahedrons of aluminum. The distances are here for gadolinium and aluminum are 3.96 angstroms, and gadolinium sulfur is 3.60 angstroms. So, in general, our proposed structure for the adsorbed gadolinium sulfate in the surface of basaluminite is monodentate binuclear. This is because in the experiment we ended up deducing that the only reaction that was occurring was the monodentate one. So, using when we model with when we adjust our theoretical spectra with Artemis in the Demeter package, the model optimized the gadolinium oxygen path, and it changed it from 8 to 10, so 10 oxygen surrounding the gadolinium. It changes the interatomic distances a bit from 2 paths, and the gadolinium, aluminum, and gadolinium sulfur interatomic distances were changed a bit, but were more or less in the same value. Here we can see that the Weller factor, which is due to the thermal vibration of the atoms, is kind of something that gives noise to our value, and we see that the model has very low t-square, and the fittings are quite good. Although I have been only, I had only 2 weeks to model this, so there might be better models. The next step would be to test with different or other type of approaches, which would be the monodentate mononuclear one. So this is the high energy X-ray diffraction. This gives us overall structural information from all the basaluminite, not just the gadolinium. And basically, in the differential PDF, we compare the signal from a pure schwertmannite with a reacted schwertmannite to see what changes in the structure have happened. So basically, I've plotted the distances with blue of our model of exhaust. The path, they are not observed because the concentration, the low concentration of gadolinium compared to the whole concentration of aluminium and others in basaluminite, it masks the information. But for example, we see a negative peak here, which means that our reacted samples has lesser amount of the sulfur oxygen path. This means that our sample has released sulfate. I mean, the reacted basaluminite has released sulfate into solution. This is a consequence of aging at higher pH of this mineral. Also, we observed 2 peaks at 2.16 and 2.92 angstroms that this is my guess, could correspond to aluminium sodium and aluminium chlorine paths respectively. This is because chloride occupies sulfate vacancies, since the aluminium sulfate distances are in 3 angstroms, but since we have released sulfate and there should be a peak here, but there is not, so there is another thing occupying its vacancy, which is one could be chloride. And the other is that sodium replaces the protons of the surface of basaluminite, and we make with ICP we measured the quantity of chloride and sodium, and we saw that there is some loss respect to the rest of these 2 elements respect to the initial solution. So, as a concluding remark for the badges experiments, we have seen that ionic strength doesn't affect the capacity to absorb the rare earth elements on the capacity of basaluminite to absorb the rare earth elements. And we see that the equilibrium constant at different ionic strength are similar to each other and of the same as earlier data at nearly no ionic strength. And for example, in high energy X-ray diffraction, we see that the exact speeding predict that gadolinium might form monodentate binuclear bindings with aluminium octahedrons at the surface of basaluminite. We also have seen that the predicted paths are not observed in the differential PDF due to the low concentration of gadolinium in the sample. However, we see some peaks that might correspond to the incorporation of sodium and chloride or chlorine into the structure. And in the reacted basaluminite, we see that the sulfur oxygen peak shows less intensity due to the loss of sulfate. Thank you for your attention, and if anyone wants to ask a question, I will be glad to answer. Okay.
Any question? I have a question regarding the sorption on schwertmannite. That you see this intermediate in the model of the experiments, you see this intermediate value of n. Then you say that, I mean, I imagine that difference between the different heavy, middle, and light rare earth elements is in the log K value, main difference. So heavy soak more and light soak less.
Yes.
Is there also a pattern with respect to the value of N? Does value vacuum also have a pattern with heavy,
Yeah, this is called the lanthanide contraction. It is due to the ionic radius of depending of which rare earth elements. It might change a bit the value of the N of the slope.
So you see a pattern?
Yes, it is a pattern. There is a pattern.
Okay.
Also, there is I have not. Well, you see that. Well, you see how the different lanthanide groups, which are divided into 4 groups, you see the pattern of when you plot the slopes.
Just, could you show the general adsorption reaction where you, because this one, it is always with sulfate. Is it because in your case your sulfate, let's say your metals or your lanthanide sulfate complex is most abundant? Or?
No, there has been in previous data, we have seen that neither chloride rare earth elements nor free ion species get absorbed onto the surface. So this is the only species that can potentially be in the surface of these minerals.
But your MSO4 plus is not at the surface. I mean, that's in the bottom.
Yeah, in the upper
No,
parts.
the other one, the M.
Yes.
This one. That's dissolved. Or.
They are in solution.
But this species, MSO4 plus, is in the water. It's dissolved in water.
Yes.
Why shouldn't why sulfate? Why not chloride and Cl?
This is because I will put the first one of the first. So acid mine drainage is basically very acid and with a high concentration of sulfate. This high concentration of sulfate changes the speciation and makes rare earth elements too complex with these species.
But this complex is always the highest concentration of all the lanthanide complexes.
In the acid mine
I think
drainage,
you had
yes,
some sort of speciation.
yes, I have.
This one.
Yes, mainly yes.
Yeah, okay. So indeed, well, not always. For instance, for the I don't know LU.
Yes, no.
There you have the LU 3 plus is most of them.
But this is not absorbed, so it doesn't
have a
react.
reaction. I mean,
As it gets, this is always an equilibrium. So if this species is absorbed, so there will be replaced. It will be replaced.
So the absorbed species is basically always dissolved. Is this?
Yes.
Okay, and then another thing, in all this experiment, let's say, when you do the absorption, isn't there also the effect of other species absorbing at your minerals, your schwertmannite, etc.?
We have seen there is some sodium and chlorine being absorbed into the structure of basaluminite. But this doesn't affect
It's not a lot. It's not a lot in comparison with your event.
No, it's not a lot. You have
because concentrations of lanthanide are very small. Sodium and calcium is very big.
We have I have an ICP analysis, and some of the sodium is incorporated. And previous studies have proved that basaluminite ages to non-trilonite, which is an aluminum and sodium hydroxide, I think. but it doesn't affect the reaction.
But can you say then for instance, schwertmannite has a high preference for lanthanide?
Yes, it has a higher. The problem with schwertmannite is that it is formed at very acid pHs. So in our case is well in the previous study cases, for example, this one, since this is a pH 3.5, it doesn't absorb because the pH is not the optimal conditions. But when schwertmannite precipitates in the estuary, for example, there is a tidal dynamics that may move these minerals, so they can potentially absorb this, and we are working on that. So.
Yeah, okay. Thank you. Other questions? Yes.
Well, thank you for the presentation, really interesting in the topic. I guess I have a question about the absorption of scandium. You said that the ionic strength is not playing a role. Maybe you can show the results of the batch experiment a little bit, the slide with the batch experiment. And so, for example, at low pH, you discussed in the introduction we are talking in the range between 2.8 up to 8 or something like that. And for scandium specifically, at pH around 4, then you can see a difference with respect to the ionic strength. So I just wondered how could you explain these differences? Because one of the main conclusions is that ionic strength is not playing a role, but the slope is different and the reach of pHs until 100% in basaluminite and schwertmannite was different. So
Yeah.
you have some.
Basically, you are right. There's a difference, but the difference is between the error range. So I cannot say anything about this. Rather than, well, they certainly are a bit different, but the difference, some of the error range overlaps one with another.
Mm-hmm.
So yeah, this is not representative.
Yeah, but if you extend, let's say you extend the axis of pH until 2.8, let's say.
2.8.
Because you have until 4.5 here. And so I just wonder because during the introduction, this pH, low pHs, it is some of the values we want to address.
Yeah.
And the slopes here, they look quite different, I would say. So I just wonder if you have some explanation. Maybe it's related to what Martin was saying about the possible interference with sodium or chloride. Sorry, this basis.
Probably, maybe for pHs, lower pHs, the difference could be more.
Exactly.
Yeah, and the problem is that at lower pH, for example, in basaluminite, it gets dissolved, so we couldn't say anything more. And at pH 3.5, more or less, schwertmannite starts to dissolve. So these are safe range to study.
And how about the ratios? Did you change the ratios?
The solid-liquid ratios.
Yeah,
Yeah, after it's so.
and it doesn't affect the changes between those, like.
Of course,
two
with more or less solid-liquid ratio, you will change it.
But then you can see more details maybe because sometimes you're like saturate because you have got higher ratios, so you can't see the details. So maybe we can just lower our ratios and see more detail between 4 and 5, between the low pHs.
Yeah, we could say, that's a nice advice. Thank you.
Yeah.
Okay. Okay, then thank you.